tell you about this statement here, which is called the monotonic sequence theorem. And it says that if you have every bounded monotonic just means it's increasing or decreasing as a sequence is convergent. So what this allows us to do is to answer the question of converging or diverging. All I've got to do is check, is my sequence bounded? Is it monotonic? And then the answer will be yes, it converges. Okay? So I wanted to show you some examples of sequences that would fall under this theorem. So the first sequence is going to be 1 over n. We've already said in the past that this sequence converges. We took its limit. But another way to show that it converges is using this theorem. Is this a bounded sequence? Yes. What is it bounded between? 1 and 0. Okay. So this tells me that the sequence is bounded. Now I need to know if it's monotonic, which means I need to know is my sequence either decreasing or increasing. And remember, we have two ways of doing that. You can convert it into a function if you want, or you can just use inequalities. So I'll let you choose. Which one do you want to do? Inequalities or functions? Functions. So I convert my sequence into a function. I replace n by x. And what's the derivative of this function going to be? If we were integrating, right? We just do the power rule. Negative. 1 over
1/2 x squared.
Negative 1 over x squared. Yep. You have the right power though. Is this positive or negative? It's negative. The denominator is a square, which is always positive, and I have negative 1 in the numerator. So f prime of x is going to be less than 0 on my interval 1 to infinity, which is the interval I care about. And this tells me when your derivative is negative, your function is decreasing, i.e. f of x is decreasing on this interval, which is going to tell me that if I compare fn to fn plus 1, fn plus 1, oops, wrong sign, is smaller. Because these values of n I'm plugging in are inside of that interval 1 to infinity. Okay. As I mentioned, you could also show it's decreasing using inequalities. In this case, for this example, they're equally difficult, I think. You could do either one. Okay. So the sequence, what we learned is the sequence 1 over n is decreasing, i.e. it's monotonic, I now have shown that this sequence is bounded and it's monotonic. So this theorem tells me 1 over n converges by this theorem I said, which was called the monotonic sequence theorem. So one thing I want to mention is that you could also use this theorem. Can also use this theorem on the sequence 1 over n to any power p, where p is greater than 0. Maybe greater than, oh. I'm going to say greater than 1 because I know for sure 1 is okay.